So what I want to do today is to introduce to you what I think is the world's most powerful microscope and also the world's most powerful telescope. Now, when you think of microscopes or telescopes, you think of sort of peering through some eyepiece down like that, or peering through some sort of eyepiece up like that. You probably don't think of what you see on this slide here. This slide is a picture of the region of Geneva in Switzerland. Those things at the back there, for those of you who are native Illinoisans, those are mountains. And, okay, so that's the Mont Blanc. This is downtown Geneva over here. This is the local airplane accelerator, otherwise known as the airport runway. And here, outlined in red, you have the location of our microscope stroke telescope. So it's a particle accelerator. It's about 27 kilometers in circumference, and on average, it's at a depth of about 100 meters. So in fact, from your airplane, you don't see very much. You might see one or two surface buildings, for example, this one over here, but most of the real action takes place about 100 meters underground. So what I would like to do in the course of this talk is explain why we've been building this thing, what science it is supposed to do, and I'll discuss also the progress that we've been making in this project, and in order to forestall some questions, what use it all is. So I thought I'd start off by sharing with you a reproduction of a painting by Gauguin, which I had a copy of the wall on my office when I was a graduate student, embarrassingly many years ago. So what these people here are asking are very fundamental questions. Where do we come from? What are we? Where are we going? And what I would like to argue is that the project, the Large Hadron Collider at CERN, which I showed you briefly on the previous slide, that the aim of this project is precisely to address these questions from the point of view, obviously, of a physicist. Concretely, what we try to do with projects such as our accelerator at CERN and the Fermilab accelerator just outside Chicago is we try to understand what the universe is made of. We also hope to understand the evolution of the universe, which could enable us to understand where we come from. And maybe we'll also learn a little bit about what might happen to us and to the universe in the distant future. So that's the aim of the project, which, as you see, is a connection between the physics of the very small, the microphysics, and the physics of the very large, macrophysics and cosmology. And I'll try to bring out those connections between the two during the course of this talk. So in our journey towards the very small and towards the very large, we're going to meet a number of ideas which I would just like to mention to you as we get started. So one of the issues, in fact, the primary motivation for building these large particle accelerators is to understand what matter is made of. And in fact, we have a theory for how the visible matter in the universe is constructed, which I'll describe very briefly later on. This theory has certain things which are missing elements which we hope to find with the LHC. Also, we think that there is physics beyond what we call the standard model of particle physics. For example, the astrophysicists and the cosmologists tell us that something like 80% of the matter in the universe is some form of invisible so-called dark matter, which they can't see with their telescopes. But I would claim that we, with our telescope, do have a chance of seeing this. As I mentioned, we hope by this sort of study of fundamental physics to cast some light on the way in which the universe evolves. This is because when we make our collisions in this sort of particle accelerator, we are reproducing the sorts of collisions that took place when the universe was a fraction of a second old. And I'll explain this in a little bit more detail later on. One of the sorts of issues that we can address in this way is where the matter in the universe originated. You look around you, you see matter. You see radiation. You don't see antimatter. Now, we physicists know that every matter particle is in principle accompanied by an antimatter particle with very similar but opposite properties. Where did all that antimatter go? Maybe laboratory experiments can answer that question. The universe is kind of big and old. How did it get to be that way? Maybe by understanding the early history of the universe better, we can answer the question. We know that there are 3 dimensions of space. Are those all that there are, or are there perhaps more dimensions of space? This is a possibility which is suggested in many theories of microphysics, and that might also cast some light on the early history of the universe. So the Large Hadron Collider, the LHC, the project which I showed you on my first slide, its principal jobs are to ask and hopefully answer at least some of these questions. So let's start off by looking inside matter. Now there's sometimes a misconception which I'd like to clear up. What we study with these particle accelerators is not some sort of abstruse stuff. We're actually discussing the structure of matter, the same matter that you and me and these roses are made of. And I think that we physicists sometimes fail to convey the wonder of the fact that all the visible matter in the universe is made up out of the same very limited number of constituents, which is really quite remarkable. All the variety of stuff that we see in nature is made up out of a few very small constituents that we can study in the laboratory. So you all know that matter is made up out of atoms. Atoms consist of electrons circulating around nuclei. You can think of nuclei as being a little bit like the sun in the center of an atomic solar system. Now, in the first half of the 20th century, it was realized that those nuclei could all be made out of 2 particles, the proton and the neutron. And for a while, physicists thought that protons, neutrons, and electrons were basically all the elementary particles that there were. In fact, what happened in the second half of the 20th century was people first of all realized that protons and neutrons were not alone. There were many other similar types of nuclear particles. And then they understood that these nuclear particles could all be understood in terms of a very small number of particles called quarks. So the frontiers of our current knowledge are electrons and similar particles, and inside the nucleus, quarks and the particles, the gluons that hold them together. So our job now in particle physics in the 21st century is to go beyond what was achieved in the 20th century and try to understand in more detail just exactly what these fundamental particles are, and also to understand the forces between them. Some of the forces are relatively well known, for example, electromagnetism, which holds those electrons in orbit around the atoms. Gravity, of course, that's also well known, but some of the other forces may not be so familiar to you. So I thought I would just briefly review with you 1 or 2 aspects of the search which revealed to us, or the searches that revealed to us some of these elementary particles. In fact, the first elementary particle to be discovered was the electron. It was discovered right towards the end of the 19th century. In fact, it's sort of ironic that just around the time when physicists finally got themselves convinced that matter was made out of atoms, Thomson, whom you see here, discovered that actually atoms were divisible and they had these electrons inside them. The apparatus that he used to show this is much like a traditional TV set. I used to be able to omit the word traditional, but nowadays, with all these plasma displays and so on and so forth, I have to sneak in the word traditional. So the old-fashioned TV sets had this sort of conical thing sticking out the back. And this conical thing sticking out the back was actually a primitive particle accelerator. It would do the same sort of job that Thomson's apparatus did. It would take an electron out of an atom and then accelerate it using electric and magnetic fields to strike the screen at the front. And then the image on the screen, well, that was what you saw. So particle accelerators are much like that. We extract electrons or protons out of the interior of atoms, we accelerate them, and then we either hit a fixed target or we hit these particles against each other and try to see what is produced. Now, many of the different types of elementary particles were first discovered in the cosmic radiation. As you probably know, the Earth is bathed in energetic particles coming from outer space. In fact, these were discovered a little under a century ago by Mr. Hess here, who's going up in his balloon. He went up in his balloon and discovered that up in the upper atmosphere there were all these charged particles raining down. Subsequent experiments showed that these particles produced many other different types of particles. The study of these things was a little bit haphazard in the first half of the 20th century, which is why sometime around the turn of the century, big accelerator laboratories were first constructed. And in particular, CERN, the European laboratory where I work, was founded in 1954 in order to study in more detail, under controlled laboratory conditions, the natural phenomena of elementary particles. Let me just mention one particular discovery that was made initially in cosmic rays and then followed up in particle accelerators. So I already mentioned antimatter. So this was actually first predicted theoretically about 80 years ago, and shortly afterwards, the first particles of antimatter, the positrons, the antiparticles of electrons, were discovered in cosmic rays. And here is Anderson with his apparatus that he used to discover these first antimatter particles. So these things have the same mass, but the opposite charge as conventional electrons. Now, for many, many years, the existence of antimatter was a sort of academic curiosity. But in fact, now they're used regularly in medical diagnosis, and this is actually something that I'll come back to towards the end of my talk. So that's just an example of how even totally abstruse discoveries might actually turn out to be useful for real people like you, as opposed to physicists. Okay, so these studies, first of all with cosmic rays and then followed up in more detail with particle accelerators, led us to what we call the standard model of particle physics. And I'll just summarize it very briefly on this slide. So what you see here are the fundamental particles of matter. So we already met the electron. For a reason which we don't understand, the electron is followed by two heavier particles, very similar but just larger masses. Over on the left-hand side here, we have the quarks. These are the constituents of nuclear matter. In fact, the regular stable nuclei could be made up out of just two different types of quark called up and down, but in cosmic rays and in collider experiments, 4 more quarks have been discovered. We don't know why there are 3 electron-like particles. We don't know why there are 6 quarks, and that's one of the big mysteries that, well, we might get some insight from the LHC. The bottom half of the slide, you see the 4 fundamental interactions. Gravity and electromagnetism, and then 2 forces that act inside the atomic nucleus. The strong force, which holds nuclei together most of the time, and the weak nuclear force, which causes some particles to decay. It's actually the interplay between these 2 forces which enables the sun to shine. So although we don't necessarily like the idea of nuclear forces, in fact, they're absolutely essential for our existence. So what you see on this slide contains enough information when you go through the physics, go through the maths, to explain all the visible matter in the universe. And for that reason, I like to refer to it as being the cosmic DNA. So I said cosmic DNA, in particular, all the stuff in the universe, the visible stuff in the universe, is made out of what you saw on the previous slide. So here's a picture of the evolution of the universe. We're up here somewhere on an insignificant planet orbiting an insignificant star in an insignificant galaxy among 100,000 million other galaxies in the universe. So what we know is that as time goes on, the universe is expanding. The laws of physics, which we understand, enable us to describe what happened back in the very early stages of the Big Bang. Now, I hasten to say, not back to time equal to zero. Time equal to zero, in fact, the physics that we understand breaks down. So we're modest people. We're not going to go back to time equal to zero. We're going to go back to just an infinitesimal fraction of a second after the Big Bang. So very briefly, this is a history of some of the important events in the evolution of the universe. So somewhere around 300,000 or so years after the Big Bang, that was when atoms were formed. Before then, the universe was so hot and so dense that matters could not exist. They just dissolved instantaneously. So atoms contain nuclei. In fact, there weren't any nuclei at all when the universe was less than 3 minutes old. They also were dissolved by the very high temperature and pressure. Nuclei are made out of protons and neutrons, but if you go back before the universe was a microsecond old, then even protons and neutrons didn't exist, and what you had was some sort of soup made up out of quarks and other elementary particles. Now, what I've described up to now is what we think we can describe using the known laws of physics. What the LHC will be able to do, we think, is to take us back to a picosecond, so that's a millionth of a second after the Big Bang, and reveal to us the physics that was going on at that time. For example, where the masses of the elementary particles came from, and many other questions. So I talk here about the masses of elementary particles. This is one of the key issues confronting particle physicists today, and so I'd like to take a little bit of time out to describe this to you. So the question here is, why do things weigh? Well, some of you may not have gone through high school yet, but those of you who did go through high school surely remember that Newton taught you that weight is proportional to mass. And even if you haven't been through high school yet, I'm sure you know E equals mc squared. Einstein told us that energy is related to mass. However, these two honorable gentlemen unfortunately forgot to tell us what mass actually is. They related other things to mass, but they didn't give us a fundamental explanation of where the mass comes from. And that's where this distinguished gentleman comes into the picture. This is Peter Higgs, theoretical physicist who has a theory for where the mass comes from. And here's his theory on the blackboard behind him there. And memorize it, because there'll be an exam as you leave the room. There won't, but... So according to his theory, there is a particle, which we call the Higgs boson, which is at the origin of the masses of all the elementary particles. And obviously we want to find this particle because it plays such an important role, and so it's become, in some sense, the physicist's holy grail. Now, I recommend that you look up Higgs boson on Google, because you will find that Higgs boson is also a jazz musician. I might mention that many of the ideas that Mr. Higgs has been playing around with were behind one half of last year's Physics Nobel Prize, which went to Mr. Minwoo, who is a local boy. He works up at the University of Chicago. Now, I'd like to try to give you some idea of the way in which the Higgs does its job. And since we're out here in the middle of the prairies, and since you still remember winter, let's think of a snowfield, an infinite snowfield stretching out featureless into the distance, completely uniform. This is the Higgs field, as we call it. Now let's consider a skier skimming across the surface of the snowfield. Doesn't interact with the snow, just skims across the top. This is like a very fast-moving particle without mass. Think, for example, of the photon, the particle of light. Light always travels at the speed of light. Now let's consider a snowshoer. So the snowshoer sinks into the snow, goes a bit more slowly, travels at less than the speed of light. That's like a particle which does have mass, the electron, maybe. And then finally, let's consider somebody who doesn't have any snow equipment at all, just hiking through the snow with boots on, sinks very deeply into the snow, moves very slowly. That is like a particle with a very large mass. So this is just a sort of caricature of the Higgs idea, a sort of universal medium. Whether you have a mass, how much mass you have, depends on whether and how you interact with this universal medium. Now, if you think snow, what is snow made up out of? What is the quantum of the snow field? Well, that quantum is the snowflake, also known as the Higgs boson. The Higgs boson can be regarded in some sense as the snowflake of this universal Higgs field, and the job of the LHC is somehow to kick up the snow and identify this particle of the Higgs snow field. Finding this particle, if it exists, would complete the standard model of particle physics. But as I mentioned earlier on, we know that the standard model is incomplete. There must be something else. In particular, there has to be something to explain the dark matter. So what the astrophysicists tell us is that there's perhaps 5 times as much invisible dark matter as there is visible matter. So here's a typical galaxy, pretty much like our own, spiraling around. And all over here, there's the dark matter, which you can't see, or at least the telescopes can't see it. Maybe we can with our particle accelerators. How do we know that this stuff is here? Well, there's a whole bunch of different ways in which the astrophysicists have convinced themselves and us that this dark matter must exist. As I mentioned previously, those galaxies are spiraling around like that. Now, in fact, they're spinning around so fast that they should actually fly apart. They don't. Why don't they fly apart? Because there must be some additional force, gravitational force, which is holding them together. Gravitational force which is generated not by the particles that we see, they aren't enough, but by these additional dark matter particles. There's other evidence that these dark matter particles have to exist. For example, we can see blobs of hot gas. This hot gas has very high pressure. It tries to expand, but it's held in place by what? By the gravitational field created by these dark matter particles, we think. In fact, people have even seen galaxies without stars. So here you do not see the galaxy without stars. So how do you know that that galaxy is there? Well, because you look at the light coming from the galaxies behind, and it's bent by the gravitational field of the dark matter that you cannot see. There's many other observational reasons for thinking that this dark matter exists. I would claim, I'll show you an example later on, that the LHC could discover the particles of this dark matter. Now, the universe contains visible matter, but none of this antimatter, which was postulated by Dirac, whom you see in these mirror image pictures over here. Now, when the antimatter was first of all discovered in cosmic rays, then it was studied in detail in particle experiments, it was discovered that matter and antimatter don't quite behave equally and oppositely. Why not? Well, there's a description of how this can happen in the Standard Model. This description was actually provided by Kobayashi and Masukawa, who shared the other half of the 2008 Nobel Prize. Could this very small difference between the behavior of matter and antimatter be related to the fact that the antimatter has apparently disappeared from the universe, which only contains matter? Well, it's possible, but the matter-antimatter difference, which has been seen in the laboratory and which is contained in the model of Kobayashi and Masukawa, would not be sufficient to explain the dominance of matter in the universe today. That would require physics beyond the Standard Model. It's physics that potentially the LHC could discover. Finally, on my list of fundamental questions, let me mention the search for a unification of all the fundamental interactions. So this was Einstein's dream. I find it remarkable. I know how old Einstein was in this picture. He was 6 years old or something like that. But you can see in his eyes the same sort of sad expression that he had 70 years later. Sad? Well, sad because he didn't make a unified theory of the fundamental interactions. He tried. This is his last blackboard, but no banana. Now, he played with various ideas for how you could construct such a unified theory. One of those ideas was that there might be additional dimensions of space. Normally we think there are just 3 dimensions of space, up, down, front, back, and sideways. But if you look deep inside matter, it's possible there might be additional dimensions of space. And this is very popular in some of the current theories of unification based on string theory. And this is something which maybe we could find with the Large Hadron Collider, the LHC. So I've described to you some of the motivations that we have for making the LHC. But before describing the LHC itself, I would just like to share with you a little bit of personal experience. Back in 1982, Mrs. Thatcher, the Prime Minister of England, came to visit CERN. And so I was introduced to her. And she asked me, "What do you do, young man?" So I explained that I'm a theoretical physicist, and my job is to think of things for the experimenters to look for. And I said, then hope they find something different. Now, Mrs. Thatcher liked things to be exactly the way that she said. So she said, "Wouldn't it be better if they found what you predicted?" So I told her that, well, if you only found what you predicted, then you wouldn't really feel that you were learning anything. The really exciting stuff is the stuff that has not been predicted. So although I've described a lot of things that we think we might find at the LHC, what I really hope is that we're going to find something completely different. Okay, so here is the microscope stroke telescope itself. So this is a view in the tunnel of the LHC. I remind you, here we are something like 100 meters underground. And as you go around the 27 kilometers circumference, you pass by 1,232 magnets contained in these blue tubes here. Now, when the LHC is operating, in each direction around those magnets will travel several thousand billion protons. Each of those protons will have approximately the energy of a fly. It'll be traveling extremely close to the velocity of light, and so it will go around this 27-kilometer ring 11,000 times per second. Now, what we hope with this circulation of these beams, two beams in opposite directions, very intense beams, we hope that we will make something up to a billion particle collisions per second, and among those billions of collisions, we hope we're going to produce the Higgs boson, dark matter, and something which we haven't predicted. So this is the official list of the things. Origin of mass, dark matter, the primordial plasma that filled the universe when it was a fraction of a second old, and to understand the matter-antimatter difference. So a few gee-whiz slogans about the LHC. So it's the emptiest place in the solar system. Inside these magnets, you have two pipes that the particles go around. They have an extremely high vacuum. In fact, that vacuum has a similar pressure to interplanetary space and 10 times lower than the pressure of the atmosphere of the moon. Of course, the moon doesn't have an atmosphere. Nevertheless, there is a small amount of gas around the moon, but we've got even 10 times less pressure than that. The magnets of the Large Hadron Collider are superconducting magnets cooled to a very low temperature. In fact, the temperature, these are parts of the cooling system, by the way. That temperature is even lower than outer space. The LHC operates, or will operate, at a temperature less than 2 degrees above absolute zero, whereas outer space is at a temperature of 2.7 degrees above absolute zero. So, well, I don't know whether size matters, and certainly the universe is a lot bigger than our accelerator, but the LHC is cooler than the universe. So, here is a cutaway view of the LHC. So, here again is our airplane accelerator over here. Here is the LHC ring in which all those particles are going to be going around. Coincidentally, the energy of the particle beams is going to be roughly the same as that of a flying airplane. Now, around these... Ooh. That's not me. Keep your fingers crossed. Somebody doesn't like our experiments.
We're going to switch to the computer up there. So if I can take this out, we have the power of the computer up in the booth.
Oh, okay.
All right.
They're going to switch to another computer. Apparently got a problem connecting.
It's more exciting when things happen you didn't predict.
Now, you're taking me too literally there. So are we ready to roll? Okay, so at 4 points around this ring, there are places where particles collide. Okay, the tool works. So 2 of these called Atlas and CMS, that's where we're going to be producing, hoping to look for things like the Higgs boson and dark matter. This experiment over here is going to be looking at the primordial plasma, and this one over here is going to be looking at differences between matter and antimatter. So when we make collisions in the LHC, if we ever get to see the next slide, yes, there we go. Those collisions produce, for a very, very brief instant, in a very, very small space, what is perhaps the hottest place in the galaxy. In fact, we estimate that within a very, very tiny volume, the temperatures are perhaps 1 billion times higher than the heart of the sun. Of course, this is only in an incredibly small space, and almost immediately that we make the collision, the particles spray apart, as you see in this picture, and not very much energy is released. After all, the energy of each particle is like the energy of a fly. So, no, don't worry, we're not actually going to blow the planet up. So here are just a few gee-whiz numbers for the LHC. Circumference almost 27 kilometers, depth about 100 meters. Another one coming. Temperature minus 271 degrees. The energy of each particle, particle physics units, it's 7 TeV. In everyday units, that's equivalent to the energy of 5 billion AA batteries connected end to end to accelerate the particle. That corresponds to the energy of a fly, and the energy is something like 7,000 times the rest mass energy of an individual proton. So the whole energy of the proton beam, as I already mentioned, is comparable to that of a flying airplane. Now, in order to produce those billions of collisions, we focus the particles down so that the beams are thinner than a human hair. And the whole thing cost, well, the material pieces cost something like $3 billion, to which you probably have to add a similar amount for the salaries of the people who assembled it, and then there's a whole bunch more for the experiments and so on. So, you know, when you add everything up, you're probably talking about not much change from $10 billion. Now, a year or so ago, I might have been embarrassed to mention $10 billion. But not anymore. Okay, so this is an example of one of the LHC experiments. This is the ATLAS experiment, which, in fact, the University of Illinois is involved with. So it's kind of big. Here's a person to show you the size. It's almost 50 meters long, 25 meters in diameter. It weighs almost as much as the Eiffel Tower. So this thing has, it's sort of designed like a cylindrical onion, and each layer of this detector is optimized for detecting a different type of particle. So it's a pretty complicated thing. It was put together by over 2,000 scientists and engineers from something approaching 40 different countries. Pretty complicated, has somebody calculated several times the number of components of a Saturn V moon rocket. So perhaps not surprising that it doesn't always work perfectly, but we'll come back to that. So this is a sequence of pictures showing the assembly of ATLAS in its underground pit. So the head of ATLAS used to like to compare this to putting together a 45-meter long ship in a 50-meter long bottle 100 meters underground. These silver things that you see here with the orange stripes, these are parts of the magnet system. And this is the final iconic image, which you must have seen a dozen times already, of some guy for scale showing you the ATLAS detector. In fact, if you go there now, you can't see inside because there's particle detection chambers all around the outside. It's basically all hermetically sealed. So you're just going to have to live with this picture. Now, I mentioned that this was put together by over 2,000 scientists from nearly 40 countries. In fact, the total number of scientists working at CERN on this and related experiments is something like 9,500. And well, here you can see the variety of countries that are involved. We've got Iranians working with Americans. We've got Palestinians working with Israelis. We've got Indians working with Pakistanis. And we've even got the English working with the French. So in order to permit all these scientists to work together, this guy here, Tim Berners-Lee, invented the World Wide Web. It was invented 20 years ago, almost exactly, in order to enable physicists to share their data. And he was working at CERN at the time, and nobody at CERN, least of all Tim, realized what a revolution in human society it was going to make. So the next time when you download from that pornographic site, please remember the guy who made it possible. What we're doing now in order to analyze the gazillions of data that are coming out of the LHC is to construct the largest computer system in the world. It's going to connect together the equivalent to something like 100,000 PCs in order to do decentralized distributing grid computing. And well, we think this is something which is going to be useful not just for particle physics, not just for other sciences, but also for other aspects of human life, although we can't actually tell you, immediately what it's going to be useful for, apart from scientific purposes. So what you're going to do with all those computers? Well, you're going to be looking for things like this. This is a simulation of a Higgs boson event. So you have to imagine that two protons have collided, one coming down there, one coming up there, produce a bunch of particles. Among them is the Higgs boson. The Higgs boson is unstable, and in this simulation it decayed into four other particles, an electron-positron pair that you see over here, and a pair of muons that you see over there. So one of the LHC collaborations is all ready for this and other discoveries. They've already got some joke papers prepared. This is a little bit optimistic if you look at the date over here, but maybe later on this year or next year it could turn out to be reality. In fact, in this joke paper, they were planning on detecting supersymmetry, planning on detecting dark matter particles. So the whole point about a dark matter particle is that you can't see it, right? It carries energy away from the event. So how can you tell that it was there? Well, it's a little bit like that Sherlock Holmes story where the most important clue was the dog that did not bark. So here you've got the picture of the detector. Some parts of the detector do bark, but this bit over here did not bark. It didn't detect any particles. So the interpretation would be that dark matter particle or particles were produced and went out through that part of the detector. So that's what people are going to be looking for. Of course, they have to be able to distinguish between that and just some, I was going to say wardrobe malfunction. No, detector malfunction. Now, here's another thing which they're going to be looking for. In some of those scenarios with extra dimensions of space, gravity, which we normally think of at the elementary particle level as being an incredibly weak force, could actually become strong. And it could become so strong that when you collide two protons, two of the quarks inside them might actually fabricate a microscopic black hole. Remember, this black hole has an energy comparable to that of two flies. Right? So this is not a big astrophysical black hole. This is a tiny little microscopic black hole, which, according to the crazy theory that says these things might be produced, would also be extremely unstable. So the way you would look for such a thing would be looking for the particles that are emitted by this thing. And here you see a simulation of what such an event might look like. Now, people have heard about black holes, and there have been a few scaremongers who said, ooh, we're going to destroy the planet. This, to use a polite word, is rubbish. Okay. Cosmic rays with much higher energies have been hitting the Earth for billions of years. They've carried out the entire LHC experimental program 100,000 times on Earth. as I speak, every second, the entire LHC program is being repeated something like 10 billion times per second, somewhere in the universe. The Earth, the Moon, the Sun, the stars are all still there. No need to worry. There is absolutely no conceivable cause for concern. The LHC is not going to destroy the planet. I couldn't resist showing this picture here. This is taken with a camera phone in a London railway station the day when we started up the LHC, and the local evening newspaper had this headline that the world survives the Big Bang when the LHC was started up. This is actually a picture of when we started things up on September the 10th. This is the control room. Everybody looks very excited and happy, except for this guy. He looks kind of young. So we achieved true fame. We featured for one day on the Google portal page, and something like a billion people watched at least some part of the LHC startup on TV. It's not often that a scientific event is watched in real time by a billion people. I'm sure that most of those billion were probably looking to see whether they're going to get blown up by a black hole. But anyway. So this is what they saw. So this little splodge of light is when the particle goes through a screen on its way around the accelerator. And the second splodge is when it comes back, having gone one complete rotation. So this was the great eureka moment. This is when everybody in the control room burst into applause, and the journalists were kind of baffled until they realized what was going on. So in those preliminary tests, we didn't actually collide the beams, but we did collide the particles in the beam with beam stops in the tube. That produced showers of particles which then went through the detectors, and in that way we were able to verify that the detector actually works. So here's one event where the Atlas detector, the one the University of Illinois is involved in, lit up like a Christmas tree when particles came through. And this is one of our collaborators. He's a sort of example of CERN internationalism, by the way. He was born in Argentina, studied in Chile, worked for many years in Germany, is now attached to a university in Israel, and is very active bringing Palestinian students to CERN. Anyway, so in this picture, he's very glad that the thing is working. Unfortunately, didn't work for very long. A few days after we started up, there was an electrical fault in the connection between a pair of these magnets. This electrical fault heated the connection up. That heating melted the connection. It broke the vacuum pipe. It broke the cryostat. The liquid helium became gas. Big problems. So these are now being repaired. The last damaged magnet has been put back into the tunnel, and later on this year we will restart operations. Considerably warier and wiser, I expect. I said that lots of people watched this on TV. This was actually the lone LHC protester who is pictured here outside the press room at the LHC startup, and somebody very kindly provided him with a journalist's coffee cup and a sandwich just to keep him going. So just to finish off, I might say a few words about what's the use of all this. Well, I would say that understanding the way the universe works is a good thing in itself. But in the process of acquiring this knowledge, you develop technologies which can then be useful, like, for example, the World Wide Web. And also the fundamental discoveries that you make may themselves turn out to be useful later on. Let me give a few examples. So, particle accelerators. there are tens of thousands of particle accelerators around the planet. Something over 90% of those, if not 99% of those, are not used for fundamental science. They're in hospitals, they're in industrial companies, they're used for practical purposes. For example, more than a half of the accelerators in the world are used for medicine, either producing isotopes that are used in medical diagnosis or used for cancer therapy. We don't only develop accelerators, we also develop detectors for seeing what these accelerators produce. And many of these detector technologies are now used, also have potential uses in medical diagnosis. I might mention the technique of positron emission tomography, or PET. This is one of the most common techniques used for localizing and studying cancers, and it actually depends on antimatter. Positron, that's the antiparticle of the electron. And not only does it use antimatter, but you also use an accelerator in order to produce this isotope, and then once you've produced it, the signature is detected by modern particle detectors. Did I remember to mention the World Wide Web? Yeah, maybe I did. Okay. Let me mention perhaps finally one or two other examples. On the left here we have Maxwell. He was the guy who formulated a theory of electricity and magnetism, which of course underlies all those mobile telephones that you all have. This guy you recognize, right? So he came up with the theories of special and general relativity. What you may or may not know is that this actually plays an essential role in GPS satellite navigation systems. The signals which are used to navigate with come from satellites. These satellites kind of high up, kind of traveling very fast. And you have to understand the theory of general relativity and the theory of special relativity in order to calculate where you are. So if you use your GPS system to get home this evening, please thank Einstein for getting you there. Another spin-off of physics at CERN is this movie that will be coming to a cinema close to you in the near future. So Angels and Demons is actually starts off at CERN, where the LHC is supposed to be producing large amounts of antimatter. Well, it won't actually do that, but okay, it makes a good story. And here is a meeting of the CERN Council. Well, it was taken from the movie, so I thought that was what it was. Maybe it's not that. This is actually a picture of Tom Hanks and his co-star and the director of the movie who visited CERN a few weeks ago. And this is another still from the movie, which actually I think looks surprisingly authentic, doesn't it? Yeah, it's pretty convincing. Anyway, I'm sure that when the movie actually comes out, there'll be another hurricane of publicity about particle physics and antimatter and CERN and the LHC, and you will be the envy of all your friends, because you will be able to tell them what it's all about, and you'll be able to explain to them about antimatter. Okay, well, that finishes what I want to say. I hope I've convinced you that the LHC is indeed not only the world's most powerful microscope for looking inside matter, but also a telescope for seeing things like dark matter that regular telescopes can't see. So, in fact, the LHC is the opposite of going back to the future. It's actually going forwards to the beginning of time. Thank you. Surely, yes. And, well, like I told you, I sincerely hope that the LHC will not find any of the things that have been predicted, and that, in fact, it will find something completely unexpected. If you look back through the history of accelerators, often they have been built in order to do one thing, but actually they become famous for doing something completely different. For example, there was a very famous accelerator at Berkeley in the 1950s that was built in order to manufacture the antiproton, and it did, but that was not what it became famous for, and in fact led to a completely new vision of what we meant by an elementary particle. There was another accelerator which in the 1960s at Stanford in California fired electrons into protons, not expecting to see very much, and it discovered quarks. So I think there's a very good chance that something completely unexpected will emerge. But if I knew what it was, it wouldn't be unexpected.
We need to wait till the microphone gets to this, so because we're recording the question.
I've had some physics students who years ago left the field of physics when the big project in Texas was shut down because there was no funding to sustain it. Will the CERN efforts go beyond anything that might have been achieved by the Texas whatever it was called?
SSC, yeah. Basically, the capabilities of the LHC are very similar to what those of the SSC would have been. The SSC would have had higher energy, but it wouldn't have had as large a collision rate. So these two things more or less cancel each other out. Now, there's also some aspects of the LHC program that were not foreseen for the SSC, although I imagine they could have done it. For example, at the LHC, we're going to be colliding heavy nuclei in order to try to reproduce the plasma that filled the universe when it was a fraction of a second old. But yes, the SSC would have had very similar capabilities to that of the LHC.
At one time, people were quite sure that atoms were indivisible. How confident are we now that quarks are indivisible?
We're not confident at all. And I can promise you that almost one of the first scientific papers that will come out of the LHC will be one telling us whether or not quarks have some sort of internal structure. It's going to be one of the first things that people are going to be looking for. So in the standard model, what's going to happen, at least some of the time, is those quarks are going to hit each other, and then they're going to bounce off each other like billiard balls. But maybe they're not actually hard billiard balls, but sort of soft, in which case they wouldn't scatter out at large angles so much. It's going to be one of the very first things that people are going to be looking for. Personally, I'm still betting on the hard billiard balls, but I could be wrong.
I think there was a question way up there. Yeah, as far as wait, we need to wait for the microphone.
Sorry.
As far as the distributed computing effort goes, can regular people get involved with that and lend our CPU time to that to help out in the computation?
In the computation for the LHC?
Yeah, the computations that go on to process all the data. You were talking about a distributed computing network?
Right. A very interesting question. So as you know, there are various ways in which people can get involved in analyzing scientific data. One is SETI at home, and there's a bunch of other things, including LHC at home. So there's an application that you can download which will analyze the trajectories of particles as they go around the LHC. And this actually was a key piece of assistance in figuring out the way in which the LHC would actually operate. Now, some of us are discussing ideas for how people could also get involved in analyzing LHC data. So this is something which is not actually gelled yet, but it's something that some of us are thinking about. But in the meantime, if you want to help out with the LHC, see if you can find this application, LHC at home, and analyze particle trajectories.
I didn't hear you mention anything about string theory. Will the results of the LHC contribute to that field, or is that over with now?
Well, one of the motivations for extra dimensions is precisely string theory. Now, string theorists, they would disagree on whether those dimensions should really be very large or whether they might just be very small. If they did turn out to be very large, then it would be possible to do fantastic tests of string theory. For example, if you produced these microscopic black holes, well, I said that they should decay through Hawking radiation. Now, Hawking radiation is normally what we call black body radiation, idealized radiation. But in string theory, that wouldn't quite be the case. There would be distortions of that radiation, and if you could measure those, that would be a wonderful way of testing those string ideas. So it's a bit speculative, but I think there are possible ways of testing string theory at the LHC.
Will we be able to predict the masses of the elementary particles? If so, when?
Well, we should be so lucky. But we have, as I described, a very developed theory of where the masses come from, which is this Higgs field. But the amount of mass that you have depends on how strongly you couple to that Higgs field. If you like, it depends on what size shoes you have as you're wading through that Higgs snow field. So we have a theory of the snow field, but we don't have a theory of shoe sizes. So we can't tell at the moment why it is that some particles weigh more than others. And this, to my mind, is perhaps one of the most difficult problems in particle physics today. So I don't know whether we're going to get more clues from the LHC. Some clues might come. For example, if there are supersymmetric particles, then the question arises, well, what size shoes do they have? Do they all have the same size of shoe, or do they have different sizes of shoes? And that could be a very important clue as to answering your question.
Well, okay. If there are no more questions, then let's thank. Oh, there's one more.
You mentioned detectors. What if there is something new, we don't have a detector for that?
Well, what the detectors have been optimized for is detecting all the particles that we know, and also the ability to tell us if there is energy that we cannot see, which would be carried away by invisible particles. Now, most of the new physics ideas would predict signatures which will be composed out of these basic building blocks of energetic particles that the detectors are well able to see. Now, of course, those detectors were designed 1.5 or 2 decades ago. And one of the challenges which I like to throw at those guys is, when we come up with some new type of particle, whether they could detect it. And let me just give you an example. A few years ago, we realized that in some theories, there might be heavy, almost stable particles, which would not be the familiar type of particle. Could the LHC detectors detect those? And so, in fact, I worked with a couple of graduate students. We analyzed what the Atlas detector could do, and actually we discovered it could do an amazingly good job of measuring the properties of those particles. So clearly, I cannot tell you how well the detectors would do for things that nobody has thought of. Right? What I can tell you is that all the things that have been thought of, even things after the detectors were designed, they should be able to find.
Let's thank John again.